everyone, and finally in this video we will introduce how do we know where the function is increasing or decreasing. That's extremely important concept and you will have it in many applications. Probably part of your career will require you to know where the profit of the business you're working with is increasing or decreasing, or the building you want to build, where the construction should go up and down and so on. Well, intuitionally speaking, suppose the function f is defined on the interval I, then we can say that on that interval function is increasing if the next value is, bigger than the previous one. So this completely makes sense. On the picture here, it looks like this. I'm going up on this graph. So if you imagine it's a mountain, you're hiking up, then you say, okay, this function, the graph of the function is increasing, at least from x of 1 to x2. Same idea with decreasing. Let me finish. Whenever x1 and x2 are in the interval, and x2 is the next value. So each next value gives me higher output. For the bigger input, you get higher output. Next input, still higher, and so on. So we're climbing up. Then decreasing means the other way around. Every time you have next input, the output becomes smaller and smaller. So this is the second graph. I'm going down. How do I know that I'm going down if I don't want to explain it with this idea of putting a pencil on a paper and literally sliding down the graph? Well, the next value gives me a smaller output. The next value gives me the smaller output. And the next value gives me the smaller output. Then the function is decreasing. And I always make a shortcut. I make increase and decrease and dot, so you will see that all the time. Too much writing sometimes. Also, idea, if a function is either increasing all the time or decreasing all the time, it's called monotonic. So this word, you heard it before, monotonic behavior, means it doesn't change. So it's just all the time goes up or all the time goes down. And we can also make a next claim that it's non-decreasing. If maybe it's increasing, so non-decreasing, it's going up, maybe stopped a little bit and keep going up. That's this little stop where derivative is 0. So we stopped, the tension line is 0. Then it's not monotonic anymore, so we say it's non-decreasing, and vice versa, non-increasing. That's why this greater or equal sign showed up. Now, well, the question for you is how to identify where the function is increasing and decreasing. We know the tools that will help us, and you're supposed to be yelling right now. I know how to find where the function is increasing and decreasing. It has something to do with slopes. Every time I say that I'm hiking this mountain up, I'm hiking like this and then like this and here, and it becomes not very hard to hike anymore. At some point it's almost flat, flattens down. What I'm talking about right now, I'm talking about slopes. When I'm talking about slopes, I'm talking about, yes, derivatives. F prime of x should be what? Positive. Whatever derivative is positive, seems like function is increasing. Whatever derivative is negative, seems like function is decreasing. Make sense? So we just basically need to find intervals where my derivative is positive or negative. And this is the theorem which called test for intervals of increase and decrease. If function is continuous and differentiable, so we can take a derivative on I, then if it's positive or at all interior points are the ones that's inside of I, not on the edges, then the function is increasing on that interval. If derivative is negative, the function is decreasing on that interval. Very nice. And still interesting that we're going to teach you to create a sine line. And the sine line will look like this. We are going to have a line which will indicate the sign of the first derivative. And then if the sign of the first derivative is positive, then the original function f is increasing. If the derivative is negative, then the original function is decreasing. If it's positive, don't drop the pencil, negative. If it's positive, increasing again, and so on. Makes sense? It doesn't have to change. But I can say that on those intervals over here, the original function is increasing. And on the other interval, it's decreasing. The original function is decreasing. The derivative sign will show me. So that's why we call it sine line. Sine line for the first derivative. Stay put because we're going to have a sine line for the second derivative later. Well, did you notice an interesting thing? If I imagine this is my hiking trail, then the function is increasing, then it's decreasing, then it's increasing again. What is happening over here? What are these points? Because how will I find those intervals without knowing what those points at all? Well, you see, something is interesting. It seems like this is the tip of the mountain and this is the pit of the bottom of the pit. Or I can say the derivatives here are 0, right? So, interesting graph over here, look at that. When I'm hiking this trail up, the function is increasing, stops, then decreases, stops, increases again, stops, and then keep increasing, right? I'll even make the same color, keep increasing. How to find those intervals? Well, you see those guys? This has horizontal tangent lines. That's where derivative is 0. F prime is 0 here and F prime is 0 here. Not only 0 though, because we know there's some kind of exceptions when we still can claim that the function is increasing and decreasing, but derivative does not exist. For example, y equals absolute value of x. Remember that at 0 there is no derivative of this function because of this cusp. This cusp tells me that f prime at 0, d and e. But it's still minimum, and also I can say that it was decreasing here, decreasing, and it starts increasing right after this cusp happened, increasing. That is why, you see those corners? I need to include those cases when f prime at those points undefined, or basically d and e. That's important. So that takes me to the first derivative test. The first derivative test will not only show me, the first derivative test will not only show me how to find where the intervals are increasing or decreasing, but also find local maximum, local minimum. Because what is happening here? This is my local maximum at this cusp, and this is my local minimum at this derivative. And here is not local minimum, so neither. Not local maximum, but derivative there was 0. Let's talk about it in a second. When I'm talking about those points, I'm talking about critical points. And that's what I'm going to write over here. Critical points, that's a very important definition. What are those critical points? You will see in the literature calling them critical points. That's x, y, so a couple. Critical values, that's just x equals a. Critical numbers, that's the same thing. So you will see different kind of ways. Values and numbers. Different books name it differently. So let's call it critical points in our case. Those points where, by the definition, I'll make it green color, it's very important. My derivative at critical point C, I'll call it C, is 0, or the derivative does not exist on the given interval a and b. That's important. Put it in the box, because definition of a critical point will be your savior for the calculus 1, 2, and 3 classes. We'll be working on this for a while, and it's a magical thing to learn. In calculus 3, we're going to learn how to use critical points in 3D. So we're going to have 3 dimensions, 4 dimensions, and so on. First derivative test. By the name, you can already guess there will be second one and maybe third one. No, third one will not happen, but second one will happen. Means we're going to use first derivative to test something. Let's see what we're testing. The function is continuous on the interval. It contains a critical point C, and I just defined what critical point is. Let me briefly write down what it means. F prime at C is 0 or f prime at c does not exist. And assume that the function is differentiable on an interval containing c and maybe c itself. So what we have here is f prime changes sign. If f prime changes sign from plus to minus, then as x increases through c, then f has a local maximum. And that's how we're going to know where the local maximum happens. If it changes from minus to plus, as x increases to c, then f has a local minimum. And f prime, if f prime is positive on both sides or negative on both sides, then f has no local maximum and no local minimum. Okay, you're thinking it's time to memorize new stuff, it's gonna be a lot of memorization. Not really. I'll help you with this. I don't like memorizing things, so I always try to visualize what is happening, and I will teach you how to build a sign line, which basically will tell you that whenever you're working with f prime, if it changed from plus to minus or from minus to plus, then the original function was increasing, then start decreasing. It makes sense that it has local maximum. Or it was decreasing and then starting increasing. It makes sense it has local minimum. It also makes sense that if the sign did not change, f prime, if the sign did not change, and for example it's still plus, then it means this point is neither local minimum, not local maximum, or minus, the same thing. Let's work through the example and you will see how it works. It's actually not that bad. For the given function, find the intervals of where the function is increasing, decreasing, and local extrema. Extrema means local extreme values or points where the function has local maximum or minimum. Look at the graph of the function. Looks like a happy dancing dude in some nightclub or something with the music. And basically from the graph, you can tell me, I can see that those are local minimums. Here's local maximum. Also putting a pencil on the graph, I can say that the decreasing part will be over here. Also decreasing over here, where my pencil is going down, you see? Increasing will be here and over here. But I will ask you, wait, so what are those points? Can you give me exact numbers? I need to know exact numbers. To know exact numbers, we need to solve this problem. And let's do it. Solutions. To find a solution, when you see that we ask you for increasing, decreasing interval or local extreme values, you always start with the derivative. The derivative of this function. Also, I would actually even start with the domain. I would say note, domain. Do you see any gaps for this function or any dangerous points? Not really, because it's first squared and then it has a cube root. Seems like all x are in a domain. Let's find the derivative of this function. Derivative of this function will be 8 over 3, 4x squared minus 4. Change the exponent, it's going to be negative 1/3, times the derivative of the function inside. That's 8x. Now what I want you to find is both where this derivative is 0 and when its derivative doesn't exist. This derivative actually has bad points, and by bad points, quote, I mean the points where the derivative does not exist because of this negative exponent over there. Let's rewrite it to see the situation. Since I have a negative exponent, 4x squared minus 4 will go to the denominator with the exponent 1/3 instead of negative 1/3. The top part will be 8 times 8, which is 64x, and the bottom has 3. This is my f prime of x. Now, very handy suggestion. Put it in the box. We will need it later. And soon we're going to be working with second derivative. So it's nice to have good notation at the beginning so that you can easily find everything. So I want to find whether this derivative is 0 or doesn't exist. Well, 0 points coming from the top being 0. D and E points coming from the bottom being 0. Make sense? So I will have to solve both. The 0 points are coming from 64x to be 0. That's where x is 0. That's my first critical point. I would even call it critical value because point is the, or critical number, both are good. Critical number, I think you will see that more, Cn. This is my input, abscissa. Now, this is the one that came from when derivative is 0. How about the cusp? You see this function actually has two cusps over here. So it means we should not ignore the situation when derivative does not exist. That comes from the denominator. 3 times 4 x squared minus 4 raised to the 1/3 is 0. Divide by 3 gives you 4 x squared minus 4 to the 1/3 equals 0. Cube both sides because the 0 is on the right hand side. I can just cube everything. 4x squared minus 4 equals 0. 4x squared equals 4. X squared equals 1. That means I have two solutions. X equals plus or minus 1. That's where my derivative does not exist. We first need to check before calling these points critical numbers, all of these points actually, the left one and the right one. Check, are these points 0, plus and minus 1 are in the domain? Because it is possible that you're looking at some points which are vertical asymptotes, and those will not be maximum and minimums and so on. We don't call them critical numbers anymore. Domain are all x. That's why I pointed out at the beginning. So I will say yes. They are in a domain, check mark. So now I will build a sign line, and it's the most important part of this video is to see the notation I do and decide if you like it. Because you will see many videos and they all have different notations. This is how I do it for many years, and I like how practical it is. I will write down the sign line for the first derivative, and I will put critical numbers, Cn, on a sign line. Also, if you have points of discontinuities, like asymptotes, put them on a sign line as well. We're going to have a long, complicated example about that later. All important points, critical points, should be on the sign line. Now, choose a test point. Test point is called a test point because it's literally testing what the sign of the first derivative is. And the test point will be plugged into this orange box. Plug here your test points. Test points to find the sign, not sign of the first derivative. Plug. So what I'm going to do, I'm going to choose some convenient points. And what are convenient points? It's up to you to decide. For example, negative 0.3 is good, or negative 0.5. I like that one. Negative 1/2. And the whole point of the theorem says you only have to check one point for the whole interval to know if the function is increasing or decreasing here. You don't have to check all the points, because the function might change the sign only before or after the critical point. So critical points shows you where the function might change the behavior. Let me take negative 0.5. So the f prime at negative 0.5, and I will be mentioning it many times. I'm looking at over there in the box. I just need to know the sign. Well, actually, why did I start with negative 0.5? You could start with any, doesn't matter. I'll put the other one higher later. So I'm plugging negative 0.5 into my derivative. The numerator, and here's a very nice notation, the numerator becomes negative, right? Negative. Because 64 times negative 0.5 is something negative. The denominator has x squared. So now the input becomes positive. But it's not important here if it's positive or negative right now. It's important if it's greater or less than 4. Well, what I know here is 0.5 squared becomes a smaller number. Times 4, it becomes even smaller. No, it's still actually pretty good number here. So you can check that the whole is, yes, it becomes even smaller. Let me check here. 4 times 0.5 squared minus 4. The whole question here, if this is positive or negative, that's what we're trying to do. Positive or negative. 4 times 0.25, right? So negative 4. Definitely, since this is a fraction, basically 1/2 squared becomes 1/4. Then, since this is a fraction, 4 becomes less. 4 multiplied by this fraction is less than 4. So minus 4 now is negative. So the whole answer is negative. The denominator is negative. Negative over negative is positive. That means the sign of the first derivative here is positive. What kind of convenient number do you want to choose here? Something that's smaller than negative 1. You can choose negative 10 or even negative 100, anything you like. Derivative or first derivative at negative 100. What's happening here? The top is negative and huge. The bottom, though, becomes positive because negative 100 squared is a huge positive number. Huge positive number multiplied by 4 is still huge. 4 and a huge number minus 4 is big number. So it's going to be positive. So the total result is negative. Negative. Probably you're thinking right now, why she's doing so complicated? Can I just take a calculator and calculate the number? Yes, but it's kind of cheating from the point of A, what if you don't have calculator? And B, it's just fun to challenge yourself to do it without calculator and not to calculate the number. I just need a sign. And it's a very nice idea that sometimes we don't need the exact number. Okay, 0.5 for this case. I will call this pink interval. So I will have f prime at 0.5. Is it going to be any different? Let's see. The top now is different. It's positive. The bottom will have the same logic we had before. The 4 times a fraction over here will be less than 4. So that number minus 4 is negative. So the whole answer is negative. And finally, 10 or 100, anything you like. Derivative of that is positive over positive. Positive over positive. That's positive. Good. Now we have signs for all possible intervals for the first derivative. And now make the sketch I just taught you before. If derivative is negative, the original function f is decreasing. If derivative is positive, the original function is increasing. Then it's decreasing. Then it's increasing. And you don't have to memorize that if it's going down and it starts going up, it means this is local minimum. If it's going up and then going down, this is local maximum. And this guy is local minimum. So now we can answer both questions at the same time. A asked me a question, the first one, number 1, asked me to find intervals where the function is increasing and the function is decreasing. So here's what I'm going to do. I'm going to look at the graph or the sign line for the first derivative I just created and read the answer. 1. The function is increasing on this interval from -1 to 0, because derivative there is positive, -1 to 0, union sign, 1 to plus infinity, 1 to plus infinity. Decreasing where the first derivative is negative, from minus infinity to 1, and from 0 to 1. Done. The second question was to find local extreme values. Well, we now know that there is a local minimum at x equals -1 and x equals 1. And there's a local maximum over there, look at that, at x equals 0. Those are only inputs for the minimum and maximum. If they ask you to find points, then there will be a last step. Plug all those points all those values you just found into a regional function to find outputs, or basically how high my outputs are. The regional function is 4x squared minus 4 raised to the 2/3 plus 4. Well, f of -1 is 4, f of +1 is 4, f at 0 is approximately 1408. So now I have couples, or the answers in terms of, in form of points. So so the local maximum and local minimum points are, local minimum happens at -1 and 4, 1 and 4. Local maximum happens at the point 0, 1408. Interesting that since the output for -1 and 1 are the same, we can check that on the graph, which is the case. It means those local minimum give you the same output. Let's go back to the graph and see the situation. Here they are, we found them. That was -1 and 1, and indeed those points have the same height. And here's local maximum at 0. Since these local minimums over here are the smallest point ever and they're the same, they actually global minimum as well. Global minimums as well. How can I classify that? Well, because on the left side the function is always going up forever if you look left up. On the right side it's always go up from left to right. Then, since it's never gonna go back, how do we know it's never gonna go back? If it would go back, we would find those critical numbers from the equation. These stop points where the function kind of stops the behavior, increasing or decreasing behavior. Since we did not find any other points, we can safely say, that's it, all the critical points are found. Then, those minimum points are the smallest points ever. Then they are global minimum as well. And I'll mention it here. Local and global minimum maximum. No, just global minimum. Maximum is local over there. And this is how we're gonna use sign line and first derivative test. Why do we call it first derivative test? Who can tell me? Because we're using first derivative. That's kind of not very tricky question. We call it first derivative test because we're using first derivative here to test the behavior of the function. And it's exactly what I just taught you. From plus to minus for the first derivative gives you local maximum. From minus to plus, it gives you local minimum. If the sign did not change plus to plus or minus to minus, the function did not achieve any local maximum or local minimum, and it looks like this. And here at this point, the derivative is 0. Before that it was positive, before that and after that it's positive. But there is no local maximum or local minimum here. Same, it will look like that. That's a cubic function, by the way. So a cubic function at 0 doesn't have any maximum or minimum, but derivative there is 0. Just imagine a little chair. And that's how you know that there's a cases when you have to be careful. Just having derivative 0 or d and e does not give you a chance to say that these are local extreme values. Those are only candidates. I will mention it over here. Make a note. Critical points are only candidates for extreme values. Since they're candidate, from this name being a candidate, you understand that it means you have to test them to know if those points are actually local minimum or maximums. To test them, you use a test. For now, we introduced first derivative test. In the future, we will have second derivative test as well. Great job for watching. I know it was a pretty long video, but it's very, very important. And I'm pretty sure you will actually enjoy this part of Calculus 1 class.